Hello guys, welcome back to another video. I am Hridayesh BY.
I am Lokesham. I am Arun.
I am Hemant.
Today in this video, we would like to present our project which we made as a part of 36-hour National Level Hackathon called quant-a-maze 2.0 organized by Q-Bits NMIT. And today our team will present all the aspects of the project. So
Let's begin. So I will be given hardware overview. This is LPU 6050 sensor, Xira accelerometer sensor. This is Arduino Uno to set to flags. This is lithium ion batteries. We have 4 relays. One is to control motor and another one is control LED. Another 2 for check the regeneration level. And we have one 12 volt DC motor with flywheels, 9 volt battery, LED strip.
Hello everyone, now let's look at the software overview of our project. We have 2 Arduinos and 2 sketches here. These are the 2 sketches and we have uploaded one in each board. And this board is to simulate the exact cornering or downhill. And this is the internal circuit where the actual region is controlled. Now let's start with the sketch in this Arduino. First line is importing the libraries, and these are the threshold values which we got after trial and error, and these are the values variables to store the smoothened values of our accelerometer and gyroscope values, and these 3 are flags. And first we will be checking whether our connection with MPU 6050 is made or not. If it is made, we will continue to the next part. Here we have initialized our GPIO pins as output mode for both coasting and downhill. This pin is for both coasting and cornering, as we has only 2 modes, that is mild and aggressive mode. Default it will be in coasting mode. And here we have 6 variables to store the accelerometer and gyroscope, all 3 axes, that is Z, Y, and X. These are the variables which store our accelerometer readings in the G units. So we have used a constant to divide our readings by to convert it to the G units to scale it down. And now we will be smoothing it using a EMA equation. The EMA stands for exponential moving average. Here we are giving weightage to both our previous value and present value. If the alpha parameter is more than 0.5 or near to 1, the smoothing will be more, and if it is near to 0, it will be very less. So it depends more on our present values. And we have 3 blocks to detect 3 conditions, that is coasting, cornering, and downhill. In coasting, if the accelerometer the smoothened value of accelerometer data is very less than the coasting threshold, then the coasting flag will be raised. And in while cornering, we have a different technique to make out that. So when it enters to the cornering mode, if the gyroscope value, smoothened gyroscope value, is more than the cornering threshold, and we have also used the false detection method, so it should not quickly get out of the cornering mode. So we have a corner stable readings count. It maintains the track of the number of counts. I'll be explaining it down. We have 3 things to notice here, that is cornering exit threshold and the number of required readings to exit the threshold, and the current stable readings count. So as soon as I enter into the cornering mode, and if my value is lesser than the cornering threshold, that means I should exit the cornering mode. So to minimize the false detection, we have given this variable. So we can change the required required readings needed. We have given it as 3. When the value is lesser than the cornering threshold, the stable reading count will get increased by 1. And if this loop repeats for 3 times, that value becomes 3, then the actual cornering will be exited. So this minimizes our false detection. Now let's jump into the downhill detection, and this works very smoothly. And we have here 8 and 2, that is inverse of tangent, and this 180 by pi is to convert the readings of this gives our radian value, so we need to convert it to angle. So we use this equation, and we have a downhill tilt threshold. If the tilt angle is greater than the downhill threshold, then downhill flag will be raised. If it is below or below the -2, this is for tolerance. So if it is below the downhill threshold, then the coasting mode will be turned on or the flag will be raised. And this is to print the serial monitor, and this is to raise the respective relays or to latch the respective relays. Now let's look into the other code, the other sketch of this Arduino. This sketch is mainly to control the motor based on the throttle values, that is whether the throttle is pressed or not. If the throttle is pressed, then the region will not be active. When the throttle is released, the region will be active. Based on the readings from the other sketch, which flag is raised, we give that data by GPIO to the another Arduino. Through this, the respective flags will be raised here. We have two relays. So for cornering and coasting one, another one is for downhill. When the throttle is released, the based on the aggressive or mild mode status, the respective loop will be connected and the region will be performed. This code is all about latching the relay, and we also have a brake light code where when the region is in aggressive mode, the brake light will be turned on, and this is the code for that.
So now I'll be discussing about the principle of working of a project. So the MPU 6050 sensor will help us determine three positions, mainly coasting, cornering and downhill. And during coasting and cornering condition, we'll be providing mild regeneration, and during downhill operation of the vehicle, we'll be providing maximum regeneration. The various levels of regeneration is achieved by using the resistor combination and short circuiting the motor terminal during regeneration mode. So once the throttle is released, one of the relays are active based on the conditions. During mild regeneration braking condition, this particular relay will turn on and will connect this 15 ohm resistor combination to the two terminals of the motor, providing mild regeneration. And during aggressive braking condition, this particular relay will turn on and will short the motor terminals and will short the two terminals of the motor, providing maximum regeneration. And during maximum regeneration, the red LED light will turn on to indicate the vehicle is slowing down at an aggressive rate and to notify other users about the same.
Now I will be giving the demo of the project. Now let's see the serial monitor of the Arduino board, and now it is in coasting. As we see the vehicle get in downhill, the downhill get on, and the cornering may be seen. It's the cornering condition also will turn on, and after that we'll come back to the coasting. Now get to this part, and this is the motor. Let us illustrate this Arduino as the moving vehicle, and this you may see the motor is running for a few seconds, and now in downhill condition, the activated, the motor gets suddenly stopped, and the red LED will get on to indicate the vehicle behind us and to alert them. And this is our overall demo of the project.